Okay, after yesterday when we started talking about conservative forces and what they were and work by conservative forces, we now have, we're going to talk about the difference between work done by conservative forces and then work done by non-conservative forces. This could initially seem to be kind of trivial, but then there are a couple of pretty important points that need to be made out of this. Okay, so, first we're going to start with the conservative forces that we do know. And the conservative forces that we have worked with so far are gravity. Okay, and our potential energy due to gravity is given by U gravity equals mg y, or mg delta y, or mg, however you want to denote your y, but it's it's generally the height above the ground is how we handle our gravity, or it's the change in height for our gravity. And the other one is springs, okay, where we have, so this E should be our elastic potential, and that's given by 1/2 kx squared. Okay, whatever these are, we also came up with this idea of mechanical energy. Mechanical energy, which is E, and this is defined as our kinetic plus our potential. All right, so okay, so we're going to take it to 2 points here. We're going to have a point here, A, and then we're going to take a point up in the air that is above ground, B. So we'll call this A and call that B. And if we're going to move an object, okay, lift it up into the air from A, but it's also offset a bit over. But if we're going to take care of this, then we're going to have, we could do this in a straight line. We could go straight from A to B, okay, and just do that in a straight line. And whatever the case is, if we're doing this with respect to gravity, then we could have that as our that would be our x direction, and we would have this, okay, as our y direction. But since the force of gravity only works in the vertical direction, only it works in the y direction, any kind of, if we're trying to study the work done by gravity, anything in the x direction is going to give us an I hat dot j hat situation, and so the total work by gravity in the x direction equals 0. Well, this is a pretty important idea, because if the work done by gravity equals 0, then we could take a path that goes like that, right? And if the work done by gravity, that means that, if we come up here, out this way, and then we come back down here, then the positive work that the gravity is doing here is going to equal the negative work the negative work that it does going up is equal to the positive work that's doing going down, and same thing down here, all the way to this point where the only work that's done is given by our work in the y direction. Yeah? So that means that, and here's the concept here, is that for and this also works for rubber bands, and so I kind of need to do a visual for you guys that I can't record on the screen. But if you take something that works, like this, we have this. Okay, so if I were to take a rubber band and I were to do the same thing with a rubber band, you'll see that it doesn't make that much of a difference. So here's my rubber band here, and I'll have it flat, and there's nothing stretching it right now, so there's no work done by the spring, or by this spring rubber band, it's a stretchy thing. Okay, but if I pull it out here, and if I get to this distance, it doesn't really matter how I get there. If I'm here, then the amount of work that was done by the rubber band is the same. right? I could have just pulled straight out. Okay, if I'm over here, or if I do something, take some strange path out to here, okay, the total work that is pulling back against the work that I've done stays the same. All right, it is equal no matter how I get there. So this idea is called path independence. Okay, and that conservative forces when they do work, the work done by these forces doesn't depend on how you get from one point to the other. It is path independent. Okay, that the work done by conservative forces is path independent. It doesn't matter how you go. Now, there's another sort of cool thing that kind of goes along with this, and that if we take, let's say I take a book, all right, you take this book, and I move the book and I fling it around the classroom, and I wind up in the same spot. Because I started at A and I finished at point A, the total work done is going to equal 0. Because as much work as it took to move it away from that point, the positive work it took to move away is equal to the negative work that it took to bring it back. So the total amount of work done by the conservative force is 0. Now, there may have been other forces at play, and we're going to get to those here right now. So, if I end up where I start, the work done by the conservative force equals 0. Okay. Which brings us to non-conservative forces. Non-conservative forces are things like applied forces, so if you push on something, or, so applied, or friction. And so I'm going to bring us back to our stage here. Here is point A, down here. This is point B. Right? Or, right there. The right edge of my little pad right there. I'm going to push my eraser this way. I'll need to hold this still. Push my eraser along this way all the way to point B. Now, there is a high coefficient of friction between my surface right here and my eraser. And so it took work for me to push it from here to here. I did work, right? Now, according to what we've talked about so far, our work equals our change in our kinetic energy, right? Well, we lost some energy, right? And because we lost some energy was taken away from us. I had an applied force, I was doing work into it, and friction was acting against it as I was going. All that work that I put into it is gone, and all the work that friction put into it is gone. It's become energy into somewhere else in the system. But what if I push up to this corner and then push out to that corner? All of a sudden, this amount of work that I'm doing this way, is I'm still working against friction because friction's pushing against me. We still have the forces acting like this. But when I get to the corner, those forces turn. right? And now if I'm pushing this way, friction's going that way. And because of this, it depends on the direction in which I'm pushing the eraser. Because now the work I'm doing this direction and the work I'm doing this direction is actually additive. And the forces aren't acting in one direction only. You following me here? Okay. If friction was restricted to that direction only, okay, then it wouldn't matter where I push it, because anytime I would go this direction, I would be working with the friction. Every time I go that direction, I'd be working against the friction. And the total work would be the same no matter how I got there. But friction turns with me. And because it turns with me, it is a non-conservative force. And so, non-conservative forces and the work done by non-conservative forces, or W non-conservative, okay, is path dependent. It matters how we go from place to place when we have non-conservative forces. Okay, so let's take this eraser here. Let's create a surface. Here's our eraser, and it's above. And it's got, no. There we go. Okay, the force acting on it is mg, and it's at a height y. And it falls to a point, we'll call it right here, before it hits the ground, y, f. Okay, and so this distance right here is delta y. And so the work done by this conservative force, okay, is equal to mass times gravity times delta y. Okay, and so when a conservative force does work, you lose potential energy from that conservative force. Follow me there? If gravity is doing work and it drops it from here to here, its potential energy will decrease. Okay, when that conservative force does work, your potential energy will decrease. So in other words, okay, the work equals negative potential energy. Okay. It will also equal a negative delta U. It will also equal a positive delta K, which means that work done. Now we know that we've defined work to be our positive, our change in kinetic energy. So it's going to be positive change in kinetic energy. Okay, so the work done, right, or let's rephrase this. So delta K plus delta U equals 0. Or the work done by a conservative force does not, it's an ugly not, change, okay, the energy of a system. Okay, remember the total mechanical energy is this E. So if we have work done by a conservative force within the system, it doesn't change the total mechanical energy of that system. Okay. Which brings us to an equation that's not in your book, although it's really useful, in regards to non-conservative forces. Okay, so non-con forces, non-conservative forces. That the work done by a non-conservative force is equal to, then, the change in the total mechanical energy of the system. Okay, if your non-conservative work, okay, or non-conservative force does negative work on the system, the total mechanical energy will decrease. Okay, if your non-conservative force does positive work, your total mechanical energy will increase. Okay, this you can start with this for any energy problem that you're going to have. Okay, so this works every time. All right, and here's where it leads to. If the work done by a non-conservative force equals 0, then that means our change in our total mechanical energy equals 0. But our change in total mechanical energy is the same thing as delta K plus delta U. Right? So delta K plus delta U is our total mechanical energy, and this is still going to equal 0. Okay, I can break this up further. Okay, and this is Kf minus Ki plus Uf minus Ui. And we can regroup these to give us our K final plus U final minus K initial plus U initial. But this just becomes our total energy, right? Which is that. Okay. So that's pretty much it with our non-conservative forces. That when our non-conservative forces will take energy out of our system if they do negative work on the system, and they'll add energy if they do positive work. All right, and that's about it.